I can't hear you. You're muted.
Oh, okay.
Yes, good.
All right. We can start. Dr. Meng, we do not need to do an introduction again. Right.
That's right.
Okay. We will share our screen. Okay. Okay. So today is class 2. In class 1, we can do a very quick recap. We first talked about supervised learning, unsupervised learning, and semi-supervised learning. Supervised learning, there is a y, so we're trying to fit theta so that f uses x to predict y. In unsupervised learning, there is no y, so we're trying to get x hat instead. And semi-supervised learning is we have some y, but most of it we do not. We also talked about regression, and the most basic regression is linear regression. So linear regression, of course, we have said that it uses mean squared error. That's basically the mean squared difference between predicted and actual. So it makes a lot of sense. And there's also mean absolute error. For linear regression, we introduced how we go from data into a big matrix, and we also talked about matrix multiplication as well as all of these. So the bias, how we integrate the bias into X. And then afterwards, we talked about gradient descent. We said that the gradient is the direction of the steepest ascent. So we want to go to the minimum loss. So we do gradient descent, and then we do a little step, little step, little step, we can get to the minimum. And here is the master equation for gradient descent. Let's talk about local minimum and global minimum. And here are some math. If you know AP Calculus, please you can derive all of this yourself, but if you do not know AP Calculus, then don't worry about it. Also talk about learning rate, matching, and classification. Classification, so in machine learning, the basically the two forms of supervised learning is classification and regression. Regression is, of course, we're trying to predict a continuous number like housing price. And classification is we're trying to classify into classes. So like yes or no, 0 or 1, color, gender, spam email, stuff like that. We talked about how to evaluate these evaluation metrics. We talked about accuracy and why in some cases it might be bad. This is the confusion matrix. And we also talked about the loss function. And here are some more mathematical derivations. And the most important part of classification of logistic regression is the sigmoid function, which looks like this. We just know that logistic regression, it is basically a linear plus a sigmoid added to the end. This is some more mathematical derivation. Okay. Now, we've talked about how we train a model, which is gradient descent. We've talked about the main methods of training the model. However, let's talk about some other very important topics. First of which is data preprocessing. So we have our data, right? It is X, the matrix X. But how do we make X into a into a very good matrix for learning? Because there are some forms of data that is not good for learning, the model might get misled. There's also the bias-variance tradeoff, which is about model complexity. And this is why we need to have an appropriate model for the situation. We cannot always just use the most complex model. There's also regularization, which is a method to prevent overfitting, which is very important. Also cross-validation and just validation in general. And validation is train, validation, and test is one of those three. I'll talk about what each of those are. So let's start with data preprocessing. So data preprocessing, there are primarily three types of data, which is numerical, categorical, and ordinal. But ordinal, we do not really need to talk about it today. The main two are numerical and categorical. So numerical, of course, it is just a number, right? Like height, weight, distance, price, or temperature, all of those. And we can do math. So we can add two numbers, like we can add two distances, or we can divide. That's meaningful. However, for categorical, the mathematical operations is not really meaningful. For example, red, green, and blue. Can you say red is 1, green is 2, blue is 3? Not really, because can you do like red plus blue? That does not really make sense. Same thing for gender, for animal type, for sentiment, like happy and sad. These are not numbers, these are categorical data. And ordinal, it is very rarely seen, but these things are like grades or income level. But most of the time, grades, it can be expressed as a number. Like you got a 70% on a test. Income level, you can express it just as your income. So ordinal data, we do not really need to talk about it. Okay. For numerical data, each individual training sample will have D features, right? That's what we have said. The big X, this is N by D. So here there are N rows. Each row is a sample. And here there are D features. Each column is a feature. And xn, we have many xn's, and this little n just means one of the big N samples. So this small xn goes to big X, and then here is an xn, here is an xn, yeah. But there's a problem because we have many different features, right? For example, if we want to predict housing price, one feature could be land area, and another feature could be, for example, the number of bathrooms. So, what is a typical land area? It might be in the hundreds, right? But for number of bathrooms, it might be 3 or 2. So, they're on different scales, and that is a problem because if we're in the loss, right? The MSE loss, it the if you look at here, right? Oh, okay. Here is loss, and here is the weights. We want to try to find the weight that minimizes the loss. However, if one feature is very big than the others, then that feature will dominate the loss, right? And if that feature dominates the loss, that's not good because every feature, we cannot say, is the number of bathrooms more important or is land area more important? That we want the model to figure out on its own. But if we have land area be in the hundreds, but bathroom is just 3 or 2, then that automatically makes land area much more important, which we do not want. That's why we need to standardize along each column because it is for each feature. We're not going to say we standardize this samples 3 bathrooms and 100 for the land size. We're not going to do that because those you cannot add the bathroom and the land area together. It does not make sense. So we're doing it for each feature. We're saying for every sample, we get the number of bathrooms. So it can be 1, 2, or 3. And then we standardize that. We standardize that because we can say, oh, the mean number of bathrooms, the standard deviation, number of bathrooms, those all make sense. So we want to standardize X along each column. So as I've said before, the large scale features, they dominate the gradient updates. And we want to ensure that each feature contributes proportionally to learning. And we also have other algorithms like KNN and K-means. Those we will talk about in our third class. But these, they are based on distance. Let me just give you a sneak peek. So for KNN, it's like this. If we have many many samples right here, and then many samples right here. I want to say, okay, this green one, which so KNN is a classification model. Just say that these are class 0 and this is class 1. So for this green point, which class does it belong to? Well, KNN is K nearest neighbors. It looks at the K nearest neighbors to this green point. So maybe it is this one, this one, this one, this one, this one, this one. And it says, okay, 4 of the 5 nearest neighbors is class 1. And 1 of the 5 nearest neighbors is class 0. So of course I'm going to be class 1. So as you can see, KNN depends on distance, right? Because we're trying to find the nearest neighbor. But if this axis is land area, and this axis is the number of bathrooms, well, land area it's on the scale of hundreds, but bathrooms is on the scale of ones. So of course, land area is going to dominate distance, and that artificially makes land area more important, which we do not want. So that is why for distance-based algorithms, it's also very important to standardize data. And it turns out that gradient descent often converges faster if you have standardized features, because unscaled features with different units or ranges create long or narrow or steep ravines. So as you can guess, for land area, maybe it forms because we have seen as we've seen in these notes. So here, right? Here is the cost, or here is the loss function. It could also be called the cost function, but here's the loss function. Here is, we can say, land area. Here's number of bathrooms. But this one little pixel right here, that is much longer than one little pixel right here. So if we scale it, it might look like this. So it might look like a huge wide thing on this axis. But on this axis, it's very narrow. And if we start right here, it'll just go here, down here. The problem is this axis, the gradient only really descends on this axis. It does not really pay attention to this, which is not good. So we can see that it converges faster when they're all balanced. Okay. So we need to standardize, that's right. But how do we standardize? There are many little different methods. Most of them are quite similar. So first of all, there is the min-max normalization. So we take each point. The I means the feature. So feature I, sample n. And then we say, okay, we want to do the standardization for each feature, right? So the minimum for this feature, so if it's number of bathrooms, the minimum might be 1. And then divided by the maximum minus the minimum, which is the range. So if maximum is 5 bathrooms, then the range will be 4 bathrooms. And this one, for this sample specifically, we might have 2 bathrooms. So 2 minus 1 divided by 5 minus 1, that is 1 divided by 4. So the standardized number of bathrooms will be 0.25. And if this equals the minimum, then it will be the minimum minus the minimum, which equals 0. And if this is the maximum, then it will be the maximum minus minimum divided by maximum minus minimum, which is 1. So you can see that min-max normalization, it compresses all of the features into 0 to 1, into this little interval. And this is usually used for turning images into pixel values. So we know that RGB, R, G, and B, each of them can be from 0 to 255, but often want to squish that down to 0 to 1. But the main form of normalization we use is called standard normalization, and it uses the z-score. If you have learned statistics, especially AP statistics, you will know what it is. But if you don't, it doesn't matter. I can explain it right now. So for here is the mean. So the mean of feature I. So I, for example, is the number of bathrooms. So the mean number of bathrooms might be 2. Okay. And we see this notation is kind of big, but all it means is here is sum it all up and divided by n. So sum all of the individual feature values divided by n, which is what mean is, right? Mean is you just sum it all up divided by the total number. And here is the standard deviation. Standard deviation is a measure of, on average, how much each data point is far away from the mean. So of course, it's a measure of how far on average each point is from the mean. Here is a point. Here's the mean. We minus it. But if it's 1 to the left and 1 to the right, that is the same distance away. So how do we make it from negative to positive? Well, you can do a square, just like MSE loss, if you remember in the first class. So this, and then you average this, and then you take a square root. That is the standard deviation. And I think we've all seen this normal curve. Here is the mean. And here is 1 standard deviation to the left, 1 standard deviation to the right, 2 standard deviations to the left, 2 standard deviations to the right. And if you have learned statistics, you'll know that like from -1 to +1, that is 68%, from -2 to +2, yeah. So for every point, we minus the mean and divide by the standard deviation. So minus the mean means, okay, we have all of our data and we minus the mean. So we shift it all to the left so that the new mean will be 0. And divide by standard deviation. So we're compressing it so that the standard deviation becomes 1. So we have turned this into a 0 mean, 1 standard deviation distribution. And this is good. This is what z-score standard normalization is. It is the most commonly used thing. And one bad thing about min-max normalization is that if there's an outlier, so if there are many houses, on an average, there are 2 bathrooms. But if one house is very crazy and has 7 bathrooms, well, then every point will divide by 7. So most of the points from 0 to 1 will be in this region, and then there will be 1 point right there. That's not good. But if we have z-score normalization, the 7, it is an outlier, and it does increase the mean, but only a very little because we have all the rest of the houses are normal. So these outliers, they still affect the mean standard deviation, but they do not compress the remaining data as severely as min-max normalization. So that's why we use z-score normalization. And another very important thing is when we are training our model, right, we want to apply standardization on X. When we train it, we will split that into X train. Okay, X train and X test. X train is for training and X test is for testing. So X test is not used at all in the training process because we want unbiased. We want some We want data that the model has not seen before. Want to see how good it does on that, and that is a good test. So when we're standardizing X, we will use the mean and standard deviation of X train. And when we standardize X test, because if we standardize X train, we'll also have to standardize X test because the model has learned the standardized distributions. So for the number of bathrooms, the model knows to get numbers like 0, which is the mean, or 1, which is a little bit higher. But it does not like understand 5 or 4. Like 5 or 4 in the model's eyes means 5 standard deviations from the norm or 4 standard deviations from the norm. But if we just input that directly, then the model will not understand it. So we have to normalize X test as well, right? That's very intuitive. But we'll have to normalize X test using X trains minimum and maximum, or that's min-max norm, or the X trains mean and standard deviation. Because if we normalize it using X test, well, X test's mean might not be the same as X trains mean. So, and that's not what the model learned. So first of all, that's very inaccurate. Second of all, there is data leakage. So that is why we need to normalize X test using X strings stuff. And in code, and tomorrow in code we will show that. Standard scalar and sklearn, it first does fit transform. The scalar fit transforms X string. So it learns X strings, mean and standard deviation, and then it applies that to X test. It does not use X tests, mean and standard deviation. So that is a thing you have to watch out for. Okay. That's all about numerical data. So for numerical data, the main we can do standardization. For categorical data, can you standardize categorical data? Not really, because categorical data might be like color, right? Like red, green, red, blue, red, red. And how does that come in data? It might be like, oh, I assign red as 0, green as 1, and blue as 2. But is that appropriate? How do I know that green should be between red and blue, right? And how do I know that red and green and blue, the difference is 1? That does not make sense. Like that's quite arbitrary of an assignment. So what do we do? What is more appropriate? Well, we do one hot encoding. What does that mean? So for this column, we turn that into 3 columns, these left 3 columns. And this column means, is it red? This column is it blue? And this column is it green? So for red, it becomes 1, 0, 0. For green, it becomes 0, 1, 0. And for blue, it becomes 0, 0, 1. That is one hot encoding, and that makes all the features symmetric, right? That does not say red is 1, green is 2, blue is 3. But red is 1, 0, 0. Green is 0, 1, 0. And because this order does not matter, right? This order does not matter. So every category is symmetric and equal. Same thing as male and female, but male and female, there are only 2 categories. So this one is it male? And this one is it female? Yeah, the main thing is it removes any artificial ordering between categories. And another very little detail that is quite helpful is if we know if it's red or green, we know what it will be for blue. So if we know that red is 1 and green is 0, well, it is already red, so it cannot be blue, so blue is 0. If red is 0 and green is 1, we know it's already green, so it cannot be blue, so blue is 0. If red and green are both 0, well, we still know what blue is because blue has to be 1. So blue is entirely, if we get rid of the blue column altogether, and we just look at red and green, we can figure out what blue is. And oftentimes that is way better in machine learning models. So we drop the last one. So red, green, and blue, we drop the is it blue column because it avoids multicollinearity, and that is linear algebra term. But you just know that it is redundant information, and that is bad for the model's performance. And for like male and female, we just drop is it female. We just have is it male, and then we just have this because is it female? That column is redundant, and that hurts training. Yeah, the main conclusion is if categorical value that variable has k possible values, we only use k minus 1 binary columns to represent it. And this is to avoid multicollinearity. Okay, let's now talk about the bias-variance trade-off. And this is mainly about the complexity of a model. So a model like linear regression, not very complex. It is just a matrix multiplication and that's it. So for each of the features, we just multiply it by a weight, we plus it all together, plus the bias, that's it. So the bias of a model is the error introduced by approximating a complex real-world problem with a simpler model. And variance means the model's too complex. It is very sensitive to small fluctuations or noise in the training data set. So let's look at a visual example. Bias is like systematic error. Low bias means the assumptions the model makes are good. So if we have a linear regression model and the data looks like this, well, it is good to assume, it is correct to assume that the relationship is linear. So the model will be mostly very accurate. But if the data is parabolic, for example, like this, but we assume that the data is linear, and then we train a linear regression, it might just be like that. But that is not a good representation. And can you do anything about it? Not really, because how is a linear regression, how is a line supposed to model a parabola? So that is what bias is. Bias is approximating a complex pattern with a simple model. So that is not enough, insufficient model complexity. But variance is different. Variance is the model is too complex. So we can see it right here. We have a parabolic thing, or maybe not parabolic, maybe like square root or whatever, but it is nonlinear. And this is the optimal pattern to learn. And of course, in real life, in the real world, there will be noise. So if housing prices, right, it is not exactly the formula. So if the formula is like 2 times the number of bathrooms squared, the house cost will not exactly be that, right? In the real world, it might just increase a little bit or decrease a little bit. So it is noisy. The real world data is noisy. But we need to assume that the noise does not matter. The noise is just noise. And if we have a too complex of a model, the model might misunderstand noise. The model might say, okay, the noise is like I'm supposed to learn the noise. And then the model might fit like this. Yeah, the model predicted every one of them completely correctly. But we're not supposed to do that because the random variations, that's supposed to be noise. You're not supposed to learn noise. So that's what high variance means. And why is it variance? Because if we have another batch of houses, so this batch, these 5 houses that the model trained on, was taken from, for example, one city. If we take another 5 houses from another city, well, then it might look like this. It might still follow generally the parabola, right? It might still follow this trajectory. And this would predict very well as well. But this line, this model, it does not it is not applied to these anymore because these it did not train on. So that's what variance means. That means if I get another set of training data, this model performs badly on this one, but it performs very good on the one it trained on. So that is because for every batch of data, the noise is different. So if you're learning the noise, you're essentially learning useless things and misleading things. So if you have another batch of data, the noise is of course going to be different. So your performance is going to be bad. That is what variance means. And why and how can variance be high? When the model is too complex, it is able to learn all of the noise fluctuations. It's not good. So if we have a model that's too simple, like a linear regression, that cannot fit well on a parabola. So that is high bias. It means no matter what, it will always be bad. But for high variance, it means it is fitting too well. It is learning even the noise. But we do not want it to learn the noise, but it is even learning the noise. So it varies if we change the data, if we change the data set for a new one. That is high variance. That is caused by the model being too complex. And we want low bias, and low variance. That is the optimum we want. So we cannot just say, okay, for this, we're going to use the most complex model we know because there's a very high risk of overfitting. Okay. The underfitting is we use a too simple of a model like linear regression for a parabolic. And most of the time, we understand that, like we can foresee underfitting. But overfitting is harder to foresee and prevent. So for overfitting, there are unique ways to stop overfitting. Okay. Here is a graph illustrating all that I've said. So model complexity, over here, it is learning even the noise. It is overfitting. Over here, it is not learning the pattern correctly because it is assuming it is too simple. That is underfitting. So for bias, don't worry about bias squared. Just this is bias. Bias is high when the model is too simple, but variance is high when the model is too complex. And this irreducible error, this is just noise. This is just the test set. You'll never get 100% on the test set. So a combination of this, and this will make the test error like this. Because training error, it decreases with model complexity, right? When the model is too simple, I cannot even learn the general pattern. So the error is very high. But as I increase in complexity, it becomes this situation. I learn it too well. I'm even learning the noise of the training data set. So yeah, the training error decreased, but the test error did not decrease. Test error will increase. So what we want is this point, this optimum, this point right here. Okay. Now let's talk about feature engineering. How do we increase the complexity of our linear regression model? Because right now, we know linear regression is very simple. But if we want to use it to model housing price, which housing price is definitely not linear with land area with number of bathrooms, right? It will be nonlinear. So how do we make it more complex? How do we try to go over here a little bit? So we do it through feature engineering. And the most simple version of that is called polynomial engineering. So let's just say there is just one feature, which is land area, x1. And let's just say the real thing we want to learn is this function, y equals 2x1 squared plus 1. So the housing cost, it equals 2 times the land area squared plus 1. But we cannot approximate it with a linear regression. So what do? We manually add x1 squared as another feature. So originally the dataset was like this. There are n samples, and then there's just one feature, which is land area. So land area for house 1, land area for house 2, all the way to land area for house n. But now we add another column. So this column is still land area, but this column is land area squared. And then we use this to train the model. So what will we get? Remember that linear regression is theta 0 times 1. This is the bias term, right? This is the intercept. Plus theta 1 times x1. So this is land area. Plus theta 2. Right now we have added another feature, which is land area squared. So we have x1 squared. So now it is able to learn this because x1 squared is right here. It will just learn to have theta 2 be 2. And because it does not depend on x1, it depends on x1 squared. This will go to 0. And the intercept is just 1 right here. So this will be 1. So our final weights will be 1, 0, 2. So now we can accurately describe the training data. We can accurately learn. Yeah. And polynomials is the most simple. So if you have x1 and x2, like land area and the number of bathrooms, you can do x1 squared. You can do x1, x2, x1 times x2. You can do x2 squared. You can even do x1 cubed and x2 to the 5. But that is a little bit overkill. We can do all of these things. We don't even have to do polynomial. We can even do log or sine or all of those stuff. But usually adding polynomials, and usually we do not go above the 3rd degree. So we do not, so this is the 8th degree. This is way too much. This is the 2nd degree, 2nd degree, 2nd degree. So usually we do not go above the 3rd degree. 2 or 3 is sufficient enough. And another thing to watch out is we can only do feature engineering for numerical data, right? We cannot do housing land area squared times color, right? Color is not numerical. We cannot do polynomial regression. I mean polynomial feature engineering for categorical data. So we can only do polynomial feature engineering for numerical data. And here is another graph of the here's another figure of the bias variance trade-off. So here there's high bias because we're assuming we're assuming this is too simple. We're just assuming it's a line, but that's not good. And as you can see, what is this? Is this regression or classification? This is classification. And so this would be something like logistic regression. So here's the decision boundary. Above here, the confidence, the output, it will be 0.5 or more. About above here, down here will be 0.5 or less, right? This can be logistic regression. So here, if we just do a regular logistic regression, it will just do a linear decision boundary, which is not good. Here is the best. Here's what we want it to learn. But if it is too complex, it is able to model things like this. And yeah, this is very accurate. This reaches 100% accuracy on the training data set. But is this applicable for the test set? Will the test set also have this? No, because the fact that this green one is here is not because it's actually there's a meaningful like pattern to learn. It's just because there is some noise. So this will have a high test error. I hope we all understand the bias variance trade-off very well. Okay, and one last thing is regularization. So how do we decrease overfitting? Because complex models, they're very nice, right? They can learn very complex patterns, but we do not want it to learn noise. So how do we do that? Well, we do it through regularization. So yes, we can do feature engineering that increases the complexity of model, but we do not know which added feature will boost our accuracy, right? If you have 3 features, so housing, land area, and number of bathrooms, and let's just say neighborhood income. And then we do polynomial feature preprocessing with degree equals 2. So we can do housing land area squared, number of bathrooms squared, neighborhood income squared. Or you can combine two. For example, land area times number of bathrooms, land area times neighborhood income, or neighborhood income times number of bathrooms. So we can have all of those features. That is what we created with polynomial feature engineering. But are all of them going to be important? No, right? Only some of them will actually be good to the model. Only some of them is the real thing we want to learn. So we do not know which feature will boost our accuracy and which won't. So how do we find out? So yeah, you can see this scales up very fast because especially if you have many features and then you combine two, that is a huge boost in the number of features. And not all of them will be important. So training will take longer and we will encounter overfitting because just due to a random chance, for example, let's just say the land area times neighborhood income. Let's say that feature does not contribute anything. Let's just say due to random chance in our training data set, like due to random chance, it has a sort of a correlation that is due to noise. But we do not want the model to learn that. So what do? We do regularization. So we add something to the loss function, right? Because we're trying to minimize the loss. We try to keep the only important features and ignore the other ones. And why is this good? Because we're trying to minimize the loss, right? And yes, we can minimize this. But as you can see here, this completely minimizes it. But this is not what we want. So we add this. This basically means, okay, this is theta. What is theta? Theta is the weight. So we add each weight squared. And what does that mean? That means if all the weights are very high, if this weight is 1 and this weight is 2 and that weight is 3, then this term will be very high, which we do not want, right? We do not want all the weights to be very high. We only want the important features weights to be very high. So if we add this, we encourage those weights who are insignificant, we encourage them to be 0, while simultaneously we want the model to have high performance. So this is what regularization does. There are two balancing forces. For this one, we want to try to get it like this. But we do not want that. We want to get it like this. So by a balance of forces, we want, first of all, this is just the regular trying to minimize loss. We want to minimize this, but we also want to minimize this. So by that balance, we get to the best minimum. And there are two ways to do that. The first is L2 regression, and second is lasso. So ridge is we use theta I squared, and lasso is we use the absolute value. And lasso, and there are little differences. For example, lasso forces a lot of the thetas to be exactly 0. We can discuss that if we have time in the after the class. But here is a little thing to think about. Okay, so that is regularization. So let's do a little recap of the first part of our class and then we can take a break. So first of all, we talked about the different types of data. And then we talked about normalization, which is a very standard part. Almost for every machine learning model you train, for everything you do, you have to consider normalization. And for categorical data, we do one-hot encoding to turn categories into numbers for our model to understand. And we also remove the last one to avoid multiclinearity. And for bias-variance tradeoff, we know that if the model is not complex enough, we'll have high bias. But if the model is too complex, we have high variance. And those both are bad. We do not want underfitting, which is associated with high bias. We also do not want variance, which is associated with overfitting. So we want this this minimum right here. And to increase complexity, we can use feature engineering. To decrease complexity, we use regularization. And we have to use all of them. Right now, if for any problem that you see, all of these you should consider because these are very, like machine learning scientists, they have like thousands of machine learning models. They all use these methods and these methods work. So you always have to think about all of these when you are training the model for our competition. Okay, let's now take a 5-minute break, and then Victor will take over to talk about the second part of today's lesson. If you have any questions, please ask in the chat. You can also ask questions about the first class's lessons. Thank you. Okay, everyone, let's come back. If you have any questions, you should ask in the chat. Or you can unmute. Okay, let's get started. So now let's talk about validation. So far we know that we need to have a training and a test set. And we know that training an ML model means finding the best parameters, like the theta star, right? Given a specific set of hyperparameters, and hyperparameters are not changed. However, we should also be able to tune hyperparameters, right? For example, yesterday we learned linear regression. In linear regression, we know that a hyperparameter is the learning rate, this alpha right here. So we should be able to change this alpha. Maybe the step size is too big, or maybe the step size is too small, right? So how do we do that? Can we use the test set to tune these? It might make sense at first, but no, you cannot do that because of data leakage. And what kind of data leakage is that? It is when we tune hyperparameters, we are saying which learning rate is the best. So for the specific test set samples, if we just tailor the learning rate to those test samples, then that is basically like cheating. The test set should be a final non-biased evaluation. We cannot look at it anyhow before. So yeah, right here, if we tune hyperparameters, we're literally cheating. We're seeing which hyperparameters are the best. It's kind of like with parameters as well. So maybe on a test set, one learning rate is super good, but we cannot know that beforehand. Otherwise, we would be cheating. Okay, so here's a little summary. For the training set, it is strictly for optimization. It is strictly for optimizing our parameters to learn the internal parameters. For the test set, it is strictly used at the very end to just evaluate on unseen data. So we need to create a validation set to tune hyperparameters. So let me write right here what it typically looks like. So typically, like let's say this is all of our data. Typically, we have 15% is validation, 15% is test set, and 70% is train set. So that is what we usually do. So that is if, and this splitting is if, for example, a competition like our competition or a problem gives you full data and you need to split it yourself. But if a problem just gives you the validation set, then just use it. If a problem just gives you the training and the test set, then it is your job to create your own validation set to see if your model's good. And a lot of the times, a problem will not tell you your performance on the test set. So you have to use the validation set to know how good your model is. Okay. When we do training, we use a loss function like MSE for regression and cross entropy for classification like we talked about yesterday. And we choose a loss function that is differentiable and stable for gradient descent. However, that is not how we should tune our hyperparameters. Because if I just say, oh, the BCE loss of a logistic regression model is 0.1, that does not make any sense. But when I say the accuracy of a logistic regression model is 0.9, then I know that's very good. So the validation set, we tune hyperparameters using evaluation metric. And we also talked about all of those yesterday, like MSE for regression. MSE is both the loss function and evaluation metric. But for classification, we use accuracy, precision recall, F1 score. So now let's talk about a few algorithms for hyperparameter tuning. The first is called grid search. So grid search is we define a manual list of specific values for each hyperparameter. And we might have many. For example, learning rate is a hyperparameter, and the regularization term that we learned up here, that's also a hyperparameter. So for example, I'm going to say, oh, let's try learning rate is 0.01 and 0.1, and let's try regularization strength of 1 and 10. So for grid search, we're basically building a big grid of possible values. So for example, like the learning rate, is 0.01 and 0.1, and the regularization strength is 1 or 10, then we need to try all of these points. So that is basically a grid. We need to try every single possible combination. So the pros of that is that it is very deterministic, it's very thorough. It basically guarantees that we will find the best combination. However, it is very inefficient. And if we have already many hyperparameters and we just add one more, then there'll be a whole bunch more combinations. So that just is huge, massive computational power. That's not good. Okay, the second option is called random search. Random search is we define a statistical distribution or range for each hyperparameter. Like learning rate, we're going to sample it uniformly from 0.001 to 0.1. And we randomly select combinations from these distributions for a fixed number of total iterations. So because of this fixed number of total iterations, we can keep our search to, say, just 50 iterations. But in grid search, we have to do all iterations, so that is kind of bad. So basically for random search, we have like, for example, the learning rate is 0.01 to 0.1. We just pick a random value. And then the regularization strength is 1 to 10. We pick a random value. And we do this for 50 times, let's say. So the pros of this is that it is much more efficient than grid search, especially when some hyperparameters matter significantly more, because we do not waste time repeating identical values of one hyperparameter to just change another, right? That's what grid search is doing. But the cons of this is that it is non-deterministic and it's kind of based on luck. We do not learn from past mistakes or successes. So, but already, random search should be better than grid search. So for ML problems, if you have many hyperparameters and you want to try very many values, random search should be better. The last type of search is called Bayesian search, and it is a little bit too complicated for us to talk about in our workshop here. But basically, it's a smart algorithm that learns from previous hyperparameter combinations by building a probabilistic model of the relationship between hyperparameters and the validation performance. So it basically learns which decisions are bad and then what I should do next. So, of course, it's better than both grid and random search, but that is a little bit too complicated. And in coding, you have to import special libraries for that as well. So it's not very easy to use. Finally, let's talk about k-fold cross-validation. So here, my 70-15-15 example. What if the 15% split, what if that was not very good? What if that split did not really represent the whole data set very well? What if it just happened to contain a lot of one class and very few of the other? So what should we do? Well, we can use something called k-fold cross-validation. So here is what it does. Here's the algorithm right here. So first, we should shuffle the whole data once at the start. So let's say this is the whole data. We're going to shuffle it, so it's all random. And then we split it into k equals sections, and usually k equals 5. Usually. So, okay. Then what we will do is just we say this is used for validation and this is used for training. And then we repeat. We say now this one is used for validation and the rest are for training. And then this one's used for validation and then the rest are for training. So we just iterate this through this 5 times. So we'll get 5 validation scores, right? In the end, we just average the k evaluation metrics. And that provides a better like validation score to for a whole data set. Because maybe in this 15 split, it was kind of bad, right? So we use this average now to select the best hyperparameters using whatever search, like random search. And that's also good because, for example, you can see here, this training data set, you might worry that, oh, these 15% might be very valuable data. I also want to train on that. Well, in this k-fold cross-validation, you can see that we basically train on all data as a whole, and then as a whole performance, we have validation score. So cross validation is very good. Okay, now let's move on to, in general, how should we solve open machine learning problems, which is very related to our competition. Is we have a data set, and let's say it's classification. We want to have a high F1 score. What should we do? So this is very important, and you should always keep these 7 points in mind. This is what most ML engineers do as well. So first, we should have exploratory analysis. First, you should check missing data. So let me go to another whiteboard to kind of talk about very quickly how we should, like, if we have missing data, what should we do? So first, we can delete. That is a method. If we delete, we can delete whole rows or whole columns. For whole rows, that's usually what we do, which means that this whole sample, we do not want it. So, but the downside of that is just it wastes usable data in other columns. For columns, if we decide to drop a column, then that might be this column contains so many missing values that like it does not even provide useful information. So that's when we drop a feature. Columns are features, right? Okay, so that is the first method, is we can just delete. And that, if you have very few missing values, then you should delete. However, there's another method, is we should impute the values. So let's talk about what should we do for numerical values, features. We have four different methods. First, we can just replace their missing value with the mean or the median. And the mean is usually good if the feature is normally distributed. And you also learn that in AP statistics. The mean is very representative if the distribution is normal. But for median, it's very good if the distribution is skewed or there are many outliers. So that is just replace all missing values with the mean and the median. And the mean and median is just one number. So is replace all the values with just one number. The second method is just fill it with 0 or some random number like -999. So that might be good because the missing value might actually provide some information. It might be like for example, in the hospital, we did not collect this feature. The feature is missing because this patient is healthy. Like we did not collect a specific medical feature because this patient is already healthy. This patient should not be in the ICU, for example. He should go out now. So sometimes missing does not just, it actually provides a lot of information. So just fill it with a random thing, that should represent it well. The third method is find like the k most similar rows based on other features, and then we just average their values. So that is also quite good. So that is saying find the k most similar, like other samples in the data set. So they will not have, for example, this feature, let's say land area. They will not have land area be missing. So what do? We just average their land areas, and that's my land area. So basically, we just find k similar samples. And how do we find similar? Well, you can do many definitions. For example, the values are close or whatever. So just find the k similar samples. What is their land area? And if my land area is missing, then just I'm gonna be their mean land area. So that's very good. And the last is called forward filling. Forward filling is usually used for time series. So like if the temperature over a day is 23 degrees, 24 degrees, missing 26 degrees, then we're going to fill it with 24 degrees, not 25 degrees. Forward filling is just what is the previous, just fill it. There's also other methods like interpolation that would fill it with 25 degrees, but that is a little bit more complicated. Okay, and then for categorical variables, let's look at what we're going to do with them. So there are just basically two methods. The first is replace all missing with the mode, the most frequent. So example, for colors, the most frequent, let's say is green. Okay, then just replace all missing values with green. But that might lead to some bias, right? Okay, the second method is to replace it with another new category called unknown or like missing. That's the same thing with this one, right? The unknown feature, that like the fact that it's missing might be very helpful. Just like what I said, the medical example. The fact that it's missing might be very important. So if we replace it with unknown, that will tell the model, oh, this is a separate category. All right. So one final thing about imputing features is we should always split into train, validation, and test, and then impute. So because we do not want data leakage. So after we split into train, validation, test, let's say we want to impute numerical features. We calculate the mean in the train set, and then use that mean to impute numerical variables in validation and the test set. We cannot, just like we talked about previously for the standard scalar, for the z-score normalization, we have to use the train mean. We we even have to use the train mean on the test set. So that is very important. So for imputing, remember that we need to split first and then impute and only use the train statistics. That's a very important part of machine learning. Okay, next, let's check whether data is balanced or unbalanced. And we talked about a lot about that yesterday, like the accuracy and F1 score. So for that, there are kind of two methods to counter that. First, we can do something called stratified sampling, and that is just we try to make sure that when we split into validation and test, we try to always have some samples in the in the low represented group. For example, 95% of people have a disease, but 5% don't. Then we always try to get some of that 5%. That's stratified sampling. And another method is just using weights on the loss. So for example, if this patient, only 5% of people have this disease, then whenever I calculate the loss for such a sample, I give a higher weight so that it counts more. And if the model makes a mistake, it penalizes the model more. Okay. The next is you should always understand the data type, like numerical or categorical or a mix in the data. And you should always know the data range and the orders of magnitude. And that's very important. For example, like we said before, you should always standardize data. If one feature is in the 0.01 range, but another feature is 10,000, for example, income, salary, then we have to standardize features, right? Okay. Next, you can also generate plots to visualize data. For example, time series over time. That's very good. So you get to know what the data looks like. The next step is data preprocessing. Data preprocessing, first, like I said, normalization. The second, one-hot encoding, like we discussed. Finally, create your own validation set if none is provided, and you can choose whether to perform k-fold cross-validation. Next, basic or no feature engineering. So when you just start out with a machine learning model, we do very basic or no feature engineering. And feature engineering, but it is very important. So we provide, for example, very light feature engineering. So for models that are linear in nature, like what we talked about yesterday, and support vector machine, we'll talk a little bit about that next time. Feature engineering is needed to create nonlinear features. So like I said, squaring and product of two features. But when I say light feature engineering, I'm not saying, for example, we have 100 features. We want to do the product of every combination. That may be too much. But if you have some kind of, for example, if this is a problem is in biology, you know that these two features, when they multiply, that is like intuitive. Then you should just add that product of those two features. We don't need to add more. Okay. Finally, dimensionality reduction. We'll talk more about that next time as well. But I will talk a little bit about that right here. So for dimensionality reduction, we have two methods. The first is feature selection. So that is just select the best features. There are 100 features, but that's a little bit too much. I want maybe only 5 features or maybe 10 features. So how do we do that? Well, the first is we can remove very highly correlated features because like we previously said, multicollinearity, want to avoid that. And the second one is we want to delete features that don't really change much. So this feature doesn't even change much if I have the disease or I don't have the disease. Then is it likely to be even useful? No. So that is the second, is features that don't change much. Okay, so that's feature selection. The second is feature extraction. So for feature extraction, there are 2 methods. The most common is called PCA, Principal Component Analysis, and UMAP. So let's just talk about PCA very quick. So PCA is, let's say here is a feature X1, here's a feature X2, and maybe they look like this. But I just want to reduce that to one feature. What should I do? So let's say we have a line here. What I'll do is project this feature onto this line. Project, project. So you can see that I can represent all features using a line, right? So my line, it will become this point. It will become this point. So now I've effectively reduced 2 features into one feature. But what line is good? Well, that is what the PCA algorithm finds. It tries to have the maximum variance. For example, if I have a line like this, look at what happens. This point goes to here. This point goes to here. They're like the same point on this line. So that's very bad. That it How do we differentiate what is happening? So we want to try to keep the variance of all the features, but we also want to try to reduce features. Okay, so that's what PCA is. And PCA, first, we can prevent overfitting. That's very nice because we're trying to reduce the number of features. The second is we can speed up training because we'll go from, say, 100 features to just 5. And the last is visualization in 2-dimensional space and 3-dimensional space. So sometimes when we have 100 features, we cannot really visualize that like this. So we should use PCA to get it into 2 features, and then we can visualize it on a grid. And if they form clusters, oh, then the problem can be easily solved, right? Okay. So that's dimensionality reduction. And finally, we will use our machine learning model. So we should try machine learning models based on intuition. For example, I feel like this problem should be solved with linear models or kernel-based methods. We'll talk about all of that tomorrow, or tree-based clustering, etc. After you try machine learning models, you definitely should try other ones because we do not know which ones are the best. And then after that, you should perform more feature engineering and iteratively scale up and improve your F1 score or MSE. Okay, so finally, let's talk about so that is it for other machine learning methods. And for the last maybe 20 or 10 minutes of class, I want to show yesterday we talked about linear regression, right? So I want to show code of how to code linear regression from scratch. And we do not need this for the competition as well. So I'm just trying to show you how we code linear regression. So you do not need to fully understand the code if you do not know how to code in Python or you do not know how to code in NumPy. That's fine. I'm just wanting to show you linear regression in code. So here's the formula that we derived last time. We need to use these formulas now. That's how we update the parameters, right? Okay. So here is the Colab. And so the code is also here. So this is just PDF that also shows the code. Okay. So first, here is our function, linear regression. And it takes in X train, Y train, number of epochs like we discussed last time, just 100 epochs, and the learning rate. The learning rate, let's set it to be 1e negative 3 is just 0.001, just 1 times 10 to negative 3. Okay, so here is our SGD algorithm. And last time we learned about stochastic gradient descent, which is we update
using only one sample every time in each epoch. So here, we're going to initialize all coefficients with just 0. So let's initialize all coefficients with 0. And then this is just to keep track of the loss over time. And I'll show you the graphs later. So first, we shuffle. Because in stochastic gradient descent, if we don't shuffle, then it's always the first one will the first sample will affect it in some way, and the second sample will affect it in some way, and the third sample, we should shuffle it to be more representative. So you can see here what we're doing. Theta equals theta minus learning rate times here is basically here, right? We're replicating the y minus the real ground truth y times the x. That's the formula. If you don't really understand this code notation, that's fine, but I'm just showing you that it is doing exactly what we derived last time. Okay, and I'm just keeping track of the loss here. Okay. And then here I'll be plotting the loss, and you'll see below. Now, in the predict function, what do we do? Well, all we need to do is this. X test multiplied by self-coefficient, which is just the theta. Oh, which is just the theta. And that equation is also right here. Okay. So that is on the test set. That is prediction on the test set. Okay, finally, the score function is just to calculate the MSE. MSE, look, it is y prediction minus y test, have the power of 2, and then mean it. That's it. Okay, now let's define the data set. So our data set, we're going to have 2 features, including the bias. So it's basically just one feature, but we want to also have the bias. Let's say we have 200 training samples and 20 test samples. Here I'm just randomly generating ground truth theta, and it's theta star. And we want to try to learn this theta. So you can see here the ground truth value. It's right here. So let's also generate some X train. So X train is just the feature. So let's say it has a mean of 5 and a standard deviation of 2. That's it. And you can see the size is n trained by d minus 1. And that is exactly what we derived last time, right? The data. Okay, so right now, because I have 2 features including the bias, so the X train is actually just many rows, 200 rows by 1. That's it. And it just has like a number, maybe like 1.1, 2 point, whatever. And the mean is 5, standard deviation is 2. Let's compute the Y train. Well, let's use our ground truth values. Here's the ground truth bias, plus the ground truth weight times X train. That is exactly the ground truth Y. Let's add some noise right here so that it is non-perfect, like real-world data. Let's do the same thing for X test and Y test. So here's the ground truth Y test. So that's what we want to predict later. Okay. So now let us plot the X train and the Y train and the X test and the Y test. You can see here. Here's the X and here's the Y. And I purposely chose only one feature so that I can plot it in the 2D plot like this. So you can see that the blue points are the train points and the red points are the test points. And it forms roughly a line, but because I added the noise, it's not perfect. And that's what we want to try to get this line. All right. So next, here is z-score normalization. We defined it above. What do? Get the mean, get the standard deviation for each feature, for each column. And then all we need to do is subtract it, divide, subtract it, divide. That's it. And you can see right here, the mean is X. We do it on X train. The standard deviation, we cut it on X train. And then we subtract, on the test that we subtract this exact same mean and divide by the exact same standard deviation. So right here is what I talked about. We do not want data leakage. We do everything on the X string, and then we even use the X string mean on the X test for normalization. All right. Next, let's define a function called add bias. That's just what we derived last time. Append a column of ones to the feature matrix. So before I said it's 200 by 1, so now it's 200 by 2, and here is all 1, and here's the features with a mean of 5 and standard deviation of 2. So that's also what we derived last time. So these two lines basically do that. All right, finally, we're going to fit the model. So I want to demonstrate to you what happens when we do not do normalization. So I will show that very soon. So here I'm saying if we use z-score, if we do the normalization, then we do it. And then we update the x-string and x-test. And then here's our model. We fit it using the x-string and the updated x-string and the ground truth y-string with these specific parameters, hyperparameters. These are hyperparameters. And then we predict, model.predict. Finally, we look at the performance and we return the performance. So now here, you can see the performance. The MSE is 0.3. It's pretty good. And here is the training loss curve. You can see the training loss is going down. It's very accurate. Oh, okay. The training loss is going down like this. So you can see that over all of the epochs, the gradient descent is working. The loss is decreasing. And here's just the norm of the coefficients, just to show you that we started from 0, right? I said we initialized with 0. But gradually, we actually came to a stable value. We converged. So that's what the norm of coefficients is saying. Okay. Next, here is generate plots. So here, I just want to show you, we have the x-test and the ground truth y-test. But I want to plot our predictions on it. So we have the y prediction and the x-test. I want to show you what our linear regression line is. Then I want to show you the residuals. The residual is y-test minus y-preds. I want to show you what that looks like. So that looks like this. So here is our test set. You can see that here are all of the test points, and here is our predicted line, linear regression line. It's very accurate, right? Very good. And here's the residual plot. The residual plot, you can see it's all kind of random. And if you learn AP statistics, you also know that random residual is good. So some points, if they're above the line, like let's just look at, so if some points they're above the line, then the residual is, if like the test point's above the line, then the residual is positive because it's y-test minus y-pred. If the test point is below the line, then the residual is negative. So you can see here. And they're all centered around 0, which is good because we want it to be very close to, we want the y-test and the y-pred to be close. All right. Now, what happens if we do not use z-score normalization? Right here. I purposely turned it off. You can see that the loss is now super wonky. And it does not, and it just goes up and down, up and down, up and down. So what is that doing? Well, does that look like this case? It looks very similar to this case, right? We're just bouncing around the center, but we're not really reaching the center. And also like this case. Oh. Also like this case. Where we might be just bouncing around the corner, but we're not really actually reaching the end. Why? Because the learning rate might be too high. And why is it in this case, when I do not normalize it, the learning rate just becomes so high? Well, let's go back to our equation right here, our update equation. Update equation here, I'm multiplying by x string. And I initially said my x string, the data set right here, the mean is 5. So the values are actually pretty big. The values are like 5.0, 5.1, 5.2, 4.8. The values are pretty big. But when I scale it, when I do z-score normalization, we said the mean will go to 0. So then the x training values will be 0.1, 0.5, negative 0.2. So here, when I do not normalize it, and I multiply by the x train, this term will become very, very huge. So that my learning rate seems like I'm doing a very big step. So I must decrease the learning rate. When I do not, when I do normalize it, the x string is quite small and the learning rate is very optimal for it. So hopefully you understand why this happens. And you can also see here, this plot. It is not really converging. This plot right here. It is not really converging. It is like bouncing around. Okay. So here's the Colab notebook. I want to show you what happens when we decrease the learning rate, because I just said the learning rate for this case is a little bit too high. So now I want to show you what happens when we decrease the learning rate. You can see here. So right now I'm just going to run it all with 1 times 10 to negative 3. Okay, it just ran. You can see it's the same plots right here. But let me just turn the learning rate down. So right here, look, I'm going to make it to be 1 times 10 to negative 4. Now let's see what happens. I'm going to run all. Okay. So here is when we do use normalization. You can see here, it is more gradual. The loss function is more gradual. Why? Because the step size is smaller, right? We move very little. So the training loss is not, it'll decrease very slowly. But right here, you can see when we do not use z-score normalization, it converges very nicely right here. So this is a perfect example to show you the learning rate is very important. It's a very important hyperparameter to tune. It's a very important hyperparameter to learn about as well. Okay. So I think that is it. All right. Yeah, that is the end of the notes. Okay.
Tomorrow we will talk about class 3, which will be on we will walk you through step by step all of these steps, 7 steps that Victor has just talked about right here. We will walk you through all these steps. We will just select a random data set that you might use for our competition. Just select a random one from the internet. And we will walk you through all of these. We'll walk you through how to explore data, do data preprocessing, do feature engineering, do dimensionality reduction, do all of these. And then we will provide you with a big dictionary of all the common ML models and how to use them. Because today and yesterday, we've only talked about linear regression and logistic regression. There are way more and very fun models. For example, KNN, for example, random forest, many different things, and also different preprocessing techniques, different, like everything. We will compile it all into one big document for you to see and for you to reference while you're trying to code your project for our competition. And we just want to highlight that for our competition, you are welcome to use any ML model you want. Just please do not use deep learning. You're welcome to use AI to help you. For example, you can ask ChatGPT stuff, because of course we cannot tell you all the ML models, all about how to use them in every detail. We cannot do that in 3 classes. So we have provided you a foundation. We hope you will use AI in our competition responsibly, and you understand what it's saying and you understand what it's doing. You're not just outsourcing all your work. So if you have any questions about the competition, about class 1, about class 2, please feel free to ask in the chat. And if you do not have any questions, then we can end the class there.
Yeah, and the final note is I have already sent out the registration form and competition rules in both through email and Slack. So please register if you want. If you have friends in other states that you want to invite, that's great. In other schools that you want to invite, that's great. If they have not attended our class, that's also fine. They're free, they're welcome to participate. And there's no entry fee, but there is $500 for prizes. So that's very great. So yeah, so that is in the Slack and the email. So please make sure to look at that and register.
Okay.
And oh yeah, and that will take place on next Saturday and Sunday, so August 15th to 16th. And the deadline for the registration is August 11th, which I think is Tuesday. So please make sure you register before the deadline.
Okay. If you have any questions,
You can ask now.
yeah. If you don't, then feel free to leave. Thank
Yeah.
you.
We will stay for a few minutes.
There's a question, which is, would binary classification be categorical or numerical data? Binary classification, we're classifying a class, so we're doing 0 or 1. So classification is finding out the answer. And you use data to find out the answer, right? That data can be categorical or numerical. So for example, if you want to predict if it is a spam email or not, well, what can be a numerical data? A numerical data could be it was
Like how many words it has.
how many words it has. What could be a categorical data? If it like a Boolean variable saying if it contains the word free. So like if it does contain the word free, then it is 1. If it does not contain the word free, it is 0. So that is a categorical data. But the number of words is numerical data. So both of those you can use and you should use if your dataset provides it, you should use to classify. Because categorical data and numerical data, that is one thing, that's on the side of data. Classification and regression, that is on the side of like the model. So those are different things. You can use categorical data and numerical data for regression. You can use categorical data and numerical data for classification as well.
Yeah, so basically, do not confuse like categorical and numerical with X and Y. For classification, that is the Y is categorical. For regression, that is the Y is numerical. But the X can be both. The X can be a mix even of numerical features and categorical features, or all numerical or all categorical, etc. And the more features, the better, right? But also keep in mind feature engineering, feature extraction, everything we've talked about today. So that is the difference between like classification regression versus what we talked about today for input for X. Okay, there's another question. It is, can we elaborate the use cases for support vector machine, tree-based, and cluster in practice? Okay.
So we know that, first of all, linear regression, it is for predicting a continuous value. So Y is continuous. For the classification, it is doing a categorical Y. SVM is a classification. So what SVM does, we can see an example here. So here is some of class 1. Wait, okay. Okay. Here is some of class 2. What SVM does is it tries to find a hyperplane to separate these. And we can do feature engineering to make this hyperplane nonlinear. We can do that. That's what SVM does. So SVM is classification. And it is kernel-based. And the kernel is basically the feature engineering part. So if you want to do classification, you can use SVM. You can use logistic regression. You can use other stuff like KNN. But yeah, that is what we use SVM. And usually, if you do not know, okay, if I should use logistic or SVM or KNN, well, why don't you use all of them and compare the results? That is the standard workflow.
Yeah. And you might have noticed, wait, this is just the same thing as logistic regression, right? Logistic regression, like we talked about yesterday, it's also a hyperplane. It's also a linear boundary. So what's the difference between SVM and logistic regression? Logistic regression is we want to minimize the loss with every point. Like if we misclassify a point, there is a certain loss that we talk about is BCE, binary cross entropy, right? Logistic regression is to minimize that. But SVM works differently. SVM works like this. We want to maximize the minimum margin. So what is a margin? So margin is like, for example, here's a point and here's a point. These are two different classes. And here's our plane. Here is a margin. Here is the margin. So here you can see here is a margin, here's a margin, here's a margin. So we want to maximize the minimum margin. What does that mean? That means that this hyperplane will be very like separating, right? So that is how SVM works. SVM does not really care about all of the points. SVM only cares about the minimum margin, and it tries to maximize that.
Yeah. Okay. And as for tree-based, it is like a different realm than gradient descent, because tree-based does not use gradient descent. Tree-based models use entropy. So if you have all the data right here, tree-based is you have all this data. We find one of the features. So right now there are D features, right? We find one of the features, and then we say, okay, what is the threshold we can split the data? So let's just say we choose a categorical feature like color. Then we can say all of the things that have color red and blue move to this. All of the things that have colors green, purple, and yellow move to here. And we want to maximize information gain or entropy decrease. So here we have red, blue, green, purple, and yellow, right? But we want to split so that all of these and all of these are purer. So we want to, for example, we want to have all of the data. We want to classify if what is the thing we can classify of color? Like we want to classify if a fire is hot or cold. So like a red fire is not that hot, but a blue fire is very hot, right? So we want to split it so that most of these in here are of one label. So maybe hot fire. And most of here are of one label, cold fire. So we want to have this be relatively pure. So these two want the split to make the overall purity greater than if it was in here. So that is what tree-based classifiers do. And that is entropy. So you want to have the maximum entropy decrease. And the tree-based classifiers, it is like different. It is not better or worse than other classification method. It is different. So what you should do always is try different trees. For example, you can just use the regular decision trees classifier. But better, you can use a random forest classifier or an extremely random trees classifier. Like all of those trees, we next class the dictionary will provide, those will have a overview of what all of those different things are. But what you should do is you should try to see which one is the best. You should train a model, and then you should also try the other ones to see, oh, is this better, is that better? And then you have the best model, you have the best results, and then that will score very high for a competition. Yeah, and then for the other, there you also said clustering. So clustering, the main thing is k-means, and clustering, that is a little different. That is unsupervised learning, right? Because we have said before, unsupervised learning, that does not have a y. We're not trying to predict a label, right? So clustering.
So clustering, let's say we have like some clusters of like over here, and we have some clusters over here. So what k-means does is it tries to find a centroid for the cluster right here and right here. Tries to find a centroid so that when we have a new point, let's say it's right here, then whichever centroid is closest to, which looks like it's this one, then we label it as this cluster. That's basically all what k-means does. But you can see that sometimes that like will fail. For example, if the clusters look like this, and like another class is like this, or like concentric circles, that's also a famous like example. So if two clusters like this, then the k-means algorithm is not very good because like where should I place the centroid? Should I place it here? But then I will like get this radius. So that is bad. So in this case, we use other models, like density-based models, to like kind of like propagate. Like for example, if you like, let's say we're right here. Oh, this is close, this is close, this is close. These are all close. Then this is all one cluster. But then this little distance is very far. We do not worry about that. And then this, oh, this is close. These ones are close. Okay. So based on density, these are all should be one cluster. So that is like a density method for like very weirdly shaped.
Yeah. So about your question about the use cases. Well, first of all, the use case that of course it is dependent on your data, right? So how do you determine that? Well, of course you have to do exploratory analysis. So you have your data. Maybe it's in 100 dimensions, but you do PCA and then, okay, you get it down to 2, and then you see that it appears it's like this. Well, then you can decide on your own which is better and which is worse, which model you should use. So those are the use cases. There are very many models in the dictionary we'll provide tomorrow. It will have them all. It will have some of the use cases. So yeah, and you also should decide on your own, and you can also ask AI.
Okay. Are there any more questions? There's a question that says, how would you mix numerical and categorical data, for example, weight and gender? Also, that is, oh, okay. So let's go to a blink. Okay.
Actually, we can just do it up here when we talk about one hot encoding. So here, the color went into these two columns, right? Well, if you also have another like numerical, okay, wait, you also have another numerical data called like height, okay? And this is like 1.1, 2.1, 1.3. Well, you just have 1.1, 2.1, 1.3.
Yeah, and then that's your whole big X
Yeah,
string
the
matrix.
big X string matrix, the n by d, this d is number of features, and those features can be categorical or numerical. So for numerical, it is just the number. For categorical, you do one hot encoding. So if you have red, blue, and green, that is 3, then that will expand to k minus 1, which is 2. That will expand to 2 features. And 2 features can be right here. So there's not really any like thing about mixing. It is you can have all sorts of data in your big X string. But one thing to keep in mind is when you have one hot encoding, notice that many of these is 0, right? Like 0, 0, 0, 0, 0. So can we do polynomial preprocessing when you have many zeros? No, because when you have just one zero, anything else you times is going to be 0. So your polynomial encoding, yeah, so your polynomial encoding, like the features that you create, you engineer, most of them are just going to be zeros, which is very completely useless. So make sure to watch out for this. If you have many categorical variables, or even if you have one categorical variable, do not use polynomial preprocessing.
Yeah, generally, like categorical variables, you do not really do any feature engineering
Yeah,
on it.
you also should not do standard scalar.
Yeah, you only standardize, like above, we have said you only standardize the numerical features. So, like you can see this is under the bullet point of numerical data. So, this is like these standardized, this is not for like uh categorical
Yeah,
data.
so like you have one like 1001111. That one is like meaningful. Like you do not need to standardize that. Standardizing that does not make sense.
Yeah.
But for height and for like land area, Those, of course, you do need to standardize the scale, but this is already just 1, 0, 0, 1. It's its own thing. You do not need to standardize it.
Yeah. Okay, and then there's another question, which is, okay, there's no more questions. Okay, so if you have any more questions, you can stay. We'll stay for maybe another few minutes, but if you do not have any more questions, you're free to go.
Thank you. Okay, if you have any more questions, please ask us via email.
Or Slack.
Yeah, but for now, we're going to
End the meeting.
Okay, thank you, everyone.
Thank you.